Hello, everybody. So this week we're going to cover convolutional neural networks, and already this is the notebook for the CNN. That's the so convolutional CNN stands for convolutional neural networks, and basically this lesson was taken from this book. It's called Deep Learning with Python. So here's the link. You just have to click, and it's gonna take you straight to the book. And the libraries we're going to be using for this lesson are NumPy, OS, the Keras library. So from Keras, we are going to use sequential, dense layers, the sequential from models, and from the layers, we will be using dense, com2D, which is the convolutional layer, match pool, which is the match pooling layer, and flatten. And also, this is another part where we are going to use a pre-trained convolutional neural network, and this one is you can say one of the pioneers of convolutional neural networks or pre-trained models. This is from ImageNet, and this one is called BGG16. One of the reasons that I chose this model is that it is a small model, so that way it is faster to train using your computer. There are some other pre-trained models from Keras as well. I think, well, I added the link. Is later on during the lesson I'll show you what the link is. And other tools that we will need for this lesson are the pre-processing images, the image data generator, and also image. This one is more to visualize, to load the images, and this one is uh, particularly for training and validating the deep learning model. So later on, we'll explain what generator is and why it is good to use it, especially when training convolutional neural networks. And as usual, we will also need matplotlib to see how the images look. So I try to make everything as simple as possible. So this is the idea. This is the problem. We will be classifying pictures, and how can you classify pictures? Well, this is the way that the best way to explain it. A picture has a height, it has a width, and also has for every height and for every width, it has a pixel. It's like a matrix. You can like for example here, this is a matrix. So basically, for every matrix, you get a different value based on the color. So for a picture, have height, width, and channels. Channels represent the colors. So in this case, the picture has a 3D channel, which is RGB, which stands for red, green, and blue. You can also have one channel, and one channel is only for grayscale, basically black and white pictures. Right. So let's continue. So what we'll be doing is we're going to classify images. We're going to build a model to classify images, whether it is a cat or a dog. And the data I got it from Kaggle. You can access the data. So this is the data set. This is the website. Um, as you may see, it contains 25,000 images. But what I did, I actually took a small sample instead because I don't have a GPU. And yeah, so the data is already here. It's in this folder. So what I did, I separated the data. Like when you go into the folder, you're going to find you will find three folders. One is for test, the other one is for training, and this one is for validation. Let's say if we go into the training folder, you can find there's one folder for cats and one folder for dogs. So basically, for each class, there is a folder in each section. If you go to test, you will see the same, and in the validation folder as well. So, yeah, this is test. Okay, okay. So just to show you the data, we're going to load one picture from each class. Say I load the directory here and here as well. So here what I get is the just to make sure, yeah, I have this file here and I have this one here. So let's see how it looks. So this is the cat. You can see the picture here. It's just a picture of a cat, and this one is just a dog. So you for the image load, you can select the target size. We want the picture to be 150 times 150 width and 150 of length. The channels is 3 RGB. So how can you check? Um, so let's try this. Type cat. Let's see the type of data structure of file. So it's an image. So I can convert this image into a NumPy array. And the way that I do it is I use the image to array, and now I get the type. As you may see, now it's a NumPy array. Now every NumPy array must have a shape. So when we check the shape, it is 150, 150, and the channel. So it has 3 dimensions. So the same thing for the dog. We convert it to a NumPy array, and yeah, that's how you vectorize images to be analyzed into convolutional neural networks. Now, last week you learned about uh, how to stack dense layers to make a deep neural network. Like remember, like one layer has a given number of nodes, and another layer has a given number of nodes, and the layer from the first node communicates. I mean, the nodes from layer one communicates to the nodes of layer two, and yeah, so that way they like basically they filter everything to get one single output. Okay, now let's cover about Python generators and what to use Python generators. Because remember when we covered this lesson, the deep learning, and throughout the whole class, when every time we have to fit something, we use the fit method. Like when we're fitting a model, like we fit the data. And the way fit works is that it takes the data that is in memory. So that's why we use the Python generator. Because when you take the data that is in memory, when training a deep learning model, it can consume a lot of memory, and perhaps the computer can crash if you don't have a CPU, or it needs more memory, or because the data set you're working with can be huge. It can be a huge data set, and you don't have the computer doesn't have the capability to scale up. So this is the idea. The idea is that we use generators to fit the model. And so what a generator is, a generator, what it does is that it doesn't save the data in memory. Let's say, for example, here, what I do is I create a list. I create a list. This is a function to create a list. So as you see, and I can print every value that is in the list anytime that I want. So I can print it one more time here. It doesn't really matter because it is safe in memory. But if I use a generator instead of saving the values in memory, So what it does is that for every value that is contained in the generator, it is released one time. So basically, in a generator, you only get the value once. You cannot iterate more than one time in a generator. So let's say for example here, I make this generator, I iterate, and then when I try to iterate one more time, I get nothing. So basically, I have to redo to start all over again. So I make my generator, I print it, but when I try to print it, I get nothing. But if I use a list, because it is safe in memory, you can iterate as many times as you want. So that's the idea of Python generators, and we are going to be using the fig generator method from in our deep learning models because the data is big, and especially when working with images, you have so many parameters that the model has to learn. So let's prepare our data. In order to work with generators, we are going to use the image data generator from Keras. And what it does is that it loads a given amount of pictures for every, you can say every iteration, every time it is iterated, like when you go and here. So in order to set up the image data generator, you're gonna have to specify the directories for train, valid, and test. That's as I did here. So you see, it's in the docs cats folder, and then here you indicate that you have three folders. This is for train, for valid, and for testing. So I only create the train generator and test generator. And what I do, I rescale the images. So in a RGB, you can't even check. Let's check here, like the CAD file. I mean, let's do it here. So when the CAD shape, so we can check the maximum and the minimum. It's max CAD. So this is the idea. In RGB, the maximum value is 255, and the minimum value is zero. Zero is for totally black, and 255 is, yeah, it's the combination of colors. And what we do is that we rescale, like remember when we normalize the data, so we rescale to have the numbers, the ranges from 0 to 1. So we are only going to have decimal numbers. So that's why the rescale here. So let me think I run. Okay, I did. So when I run this, as you see in the training folder, it shows that I have 1,000 images in total, and from those 1,000 images, I have two classes, which is that's what you have to specify here, binary. And the batch size here, it says that every time I iterate over the train generator is going to release 20 images per iteration. That's what the batch size is. Okay. And same, okay, this the target size, this is the size of the image that I want. 150 by 150. So same thing, I do the same thing with the test generator where I use this one here, and the same thing for the validation generator. And it's good, yeah. So for the test generator, I have 200 images, and the same thing for the validation generator with two classes each. So that means 100 pictures of cats and 100 pictures of dogs, and same case in the validation folder as well. So this is what we're going to do. I already trained the models, and because it takes time to do it, I'm not going to run it again, but I'll walk you through. So this is where I create the first model, like here, translated. This is the first approach. So we create just that way you understand better. So we create the dense layers, and what the dense layers does is that it creates weights for, basically you can say, for grids of points in the picture. So this is the summary. It's good to run the summary, that way you know what you have. So what I did for the dense layers, I for the first layer I specified that I want 200 nodes, and as an input, this is the shape of my picture. Like, remember when we did the cat shape, or even dog? Let me do dog. So I specified the input here, and the activation for this one I choose prelude, and I add a second layer. And what the second layer does is that it, it has 200 neurons in the second layer with the activation of prelude. And the third layer is a flatten layer. So what flatten does is that it basically converts everything into a single dimension, you can say. Let's say, for example, here, like you see in the summary that I have from the second layer, this is the shape of the output file. We have 150 nodes, 150 by 150 times 200. This is the channel. This is the, yeah, the number of nodes, and the length and width of the picture. So if you multiply 150, let's multiply here, 150 times 150 times 200, that's what you get. That's what flatten does. So then all this information go into the last layer, which is the activation. In this case, is instead of ReLU, I choose sigmoid because it is a classification problem. And remember from logistic regression, where we talk about the sigmoid function, you can also choose other activation for functions ideal for classification, like the, for example, softmax or tag. Okay, so let's continue here. So instead of doing the motor like before, this is what we did: motor that fit. No, we're going to use the fit generator. If you remember what I discussed before, that instead of saving the data in memory, we're going to generate the data every time. So that for every uh, epoch, there's a number of pictures released for the model to learn from it. And this is where I trained the model. So I said that I wanted 30 epochs. Remember, the epoch means every time the model is going to be trained during the data set. Let's say if you want, so if you specify like 10 times, it's going to go over the training data set 10 times. So in this case, I said 30. And I said 20 steps per epoch. That means it's going to take the whole data set and divide it into 20 pieces. And it's going to feed those chunks into, it reaches the number of steps of 20. And then it's going to start another epoch. And the same thing for the validation generator. So it's going to divide the validation data into 15 chunks, and it's going to pass those chunks, so that way you can take like the whole average at the end. So when I train it, you see I have 30 epochs, and it specifies here 20 steps per epoch. And this is the accuracy of the training set, and this is the accuracy of the validation set. So let me scroll down. When I scroll down, at the end, clearly there is overfitting. So because I have 73% accuracy in the training set, but only 62% accuracy in the validation set. So let's remember that the validation data that the model uses here is not used to train the model. So it's only used to validate while the model is training. So what we're going to do, how can we improve and basically get rid of this overfit? Then we can add filters, because that's basically what convolutional neural networks are. They basically filter the data to extract the most important features within an image and then learn from those features. Like for example, this is the process for of how a convolutional model works. This is the convolutional layer. So let's take this example here. The convolutional layer. You have a picture. This is the picture, right? This is the input feature map. That's what it is, the picture. So as I said before, a picture has a width, has a height, it has in this case they call it input depth, which you can say are the channels. So what you can do is that you can take a small sets of the picture, like you can divide it, like basically as they have it here, input patches, either 3 by 3 or 5 by 5. You can divide it and take subsections of the picture and then multiply that by a filter or a kernel. Well, you take the dot product with a filter, which is the kernel in this case. And what the kernel does is that it basically takes everything. It shrinks the height and the width, but increases the depth. So basically, for the depth is the number of filters you have for every convolution. So after every patch is transformed by the dot product of the kernel, everything is set up to into a single volume. So basically, it's like creating, it's like adjusting the dimensions of the picture, you can say. And after doing that, like adjusting the dimensions, usually they do what is called pooling. And one of the reasons to do pooling is to decrease the size of the images. That way you can decrease the number of parameters. Remember, when we have too many parameters, we are at risk of overfitting. So pooling does decreases the number of parameters. So here this picture shows two ways of pooling. One is called max pooling, the other one is called min pooling. You can try both. For this lesson I use max pooling, and it is the most popular because it has a higher most of the time works better than min pooling. And what pooling does is that it takes a grid, like it goes to the picture. Let's say if you divide the picture in four pieces, and it goes to that grid and take the maximum value in that grid. So basically, in max pooling, what you do is that you reduce the images, the height and the width by a quarter. That's what you do by a quarter, and you see why I said by a quarter. Let me explain now. So, putting everything together, the convolutional layer and the pooling layer, you make a convolutional neural network. And this is what a convolutional neural network is. A convolutional neural network takes an image, have a convolutional layer, which uh, transforms the image, like it shrinks the height and the width, but increases the number of filters, like the depth of the image. And then you reduce the width and the height of the image by a half, well, by a quarter, using pooling. And then you continue, and at the end you're going to have a fully connected dense layers, like the one that I had in the beginning, like with 200 nodes, as many nodes as you want. And this here is showing like this image was taken from ImageNet, and it has a good article on how CNN works. So let's do a CNN from scratch in this part. CNN from scratch, this is what we do. Like as I said, so we start with the model sequential, and then we add the convolutional layer. So this is the number of channels that I want. Like I transform this into this number of channels, and the 3 by 3, this is the how I want the input patches to go. Like take 3 by 3 pieces. I'm going to use the preload activation, and for the match pooling, I'm going to take a 2 by 2 matrix and take the match of the 2 by 2 matrix. So here I transform, I increase the number of channels to 64, and here I increase the number of channels to 128. So for every convolution, I do a match pooling to reduce the number of parameters. And before connecting the output of the match pooling of the you can say the image already filtered, I flatten the file, I flatten the data, and then send connect everything to a fully dense layer. So basically the same thing that I did at the beginning, but in this part I put everything together. So as a loss, I use binary cross entropy because it's a classification, and for the optimizer, I use a stochastic gradient descent. And the reason I use a stochastic gradient descent is because since the data is not sequenced, it will be good to shuffle the data every time that is being fed to the model for every epoch. So that way you don't get trapped like into a cycle, and it's better to reach global minimum, and it doesn't get stuck into a local minimum. And yeah, the matrix of that we want as a objective is to increase the accuracy. So here's the architecture of the whole model. So as you can see, you got this number of layers. Like you see how it was decreased. Like we had 150 and 150 and 3, and here it was decreased from 1 to 148, 148 and 32. As I said, so that's what a convolutional layer does. It shrinks the height and the width and increases the depth, but it allows you to learn more from 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 the actual features. So this is the idea. Here you have a total of 7,500,000 parameters, 500,000 parameters. I mean, so when we fit the model, then the same number of epochs, stacks per epoch, and the validation steps is specified here. So when we scroll down to see how the model learned, you see we have the overfitting is much less. Like you have 63%, and here you have 59%. So, but there is still overfitting compared to the fully dense layer. And one of the things that we can avoid overfitting is that we can basically regularize the model using data augmentation. So what data augmentation is that it takes the same image, and it basically creates more images using one single picture. Let's say, for example, you can shrink the image, you can zoom in, you can flip it, you can rotate the image. So that way the model learn more, because basically you be creating data from data that you already have, and that way you increase your data set. So for this, what you do is that you specify that in the data generator. So you create another image data generator, and you specify the rotation that you want the rotation range to roll 40 degrees. Match the same thing with the width shift range and height and shift. So you'll be shifting the image a few times, horizontal flip, and yeah. So this is one example. Like remember the picture of the cat. So you see how it was rotated here. Here it was flip. and here how it was flipped and rotated. So it does a combination. This is random. It does a combination of so many things. So we okay. So we are going to do data augmentation and then retrain the model. So we specify here like we want to rescale the image and specify all the things that we want for the image data generator for the data augmentation. I mean, like the cheer range, like cheer is when you expand something. So here, this is the model created one more time, the same architecture as the one that I did above, and here I trained the model. So let's scroll down and see that there is not overfitting now based on the last three epochs, but the accuracy is too low. Basically, we are just a bit above luck, because if your accuracy is if the accuracy is point 0.5, point 0.5, that means it's luck. But if it is above point 0.5, I mean there's a higher degree of luck, you can say. So what can you do to increase the accuracy? Well, you can use a pre-trained model, and what a pre-trained model is a model that someone else trained. It is public online, and then you can use it and perhaps make some adjustments to it, and then you can use it for to make predictions in any given data set. Well, not any given data set, but I mean for in this case for images. So we are going to be using the BGG16, and Keras does offer those pre-trained models. You can access those to get more information about those models. You can go here, like the applications module, like they have ResNet, BGG16, BGG19, Inception. So yeah, you can go to YouTube, get more information. But let's talk more about this part here. So you have the pre-trained model, and what you do, you take the pre-trained model, and the weights I specify one the weights from ImageNet. That means when it was trained, yeah, like the weights that they used to, the weights the model obtained when they trained the model, it was like something about like 14 million images when BGG16 was trained. So we also specified that we don't want to include the top. That means the fully connected dense layers. So that way I can add my own fully connected dense layer and train those layers. So that way the model is specifically trained to detect images of dogs and cats. Now, I also specified the size of the input that I'm going to have. Like remember the size of every picture that I have is 150 by 150 by 3. 3 is the number of channels. So this is the whole architecture of the BGG16. You can look it up. I recommend you look it up in Google. And so it has convolutional models. So basically, let's put it like this. It's divided by blocks. It's divided into 5 blocks. So you have the input layer, and in block one, you have two convolutional layers and one match pooling. For the second block, the same thing, two convolutional layers and one match pooling. Same thing for the third layer. For the third layer, you have three match pooling, and no, I'm sorry, three convolutional layers and one match pooling. And for the fourth layer, you have three convolutional layers and one match pooling. And for the fifth block, you have three convolutional layers and one match pooling. So in total, you have 14 million parameters. So what you do, you, the way you do it, you start the model like the way that I did it here, and you add the those convolutional layers, the ones here, basically the convolutional base, you can say, to the model. I flatten the output and then connect that to a dense layer, what I have here. Same matrix for the loss optimizer and the objective matrix of the classification. So when I do the summary, this is what I have. This is the output shape of the convolutional base, the BGG16, and it is transformed into this, and then it is sent into the fully dense layer. I use the fit generator again with the same parameters. So let's scroll down, and you can see there is a huge difference here compared to the other two models. The one from the dense layers and using the CNN from scratch, even with data augmentation. I mean, we're also using data augmentation here, so I have to make a note of that. But yeah, there's a big difference. Like you see, like the accuracy here and here, like for the last, you can say what, 20 epochs, we had a good accuracy. And this is the last part where you can also play a little bit more with the pre-trained models. Let's say, for example, that if the model is not learning properly, what you can do is that you can train the layers of the models. That is something that I didn't mention, and is that, let me scroll up to the architecture of the model. So when you train the model, if you don't specify it, these layers are freeze. That means that when you are training the model, the weights here, they do not change. They stay the same. I mean, the coefficient weights, like the number that multiply by every feature within the input. So they stay the same. So if you want to change it, there's a way to change it. Let's say, for example, if we want to change, we want the last layers to adapt to the data set that we have. Like, let's say we can specify block 5, for example. Like, everything in block 5 is going to be updated, but everything below block 5 is going to be freeze. So it's not going to learn everything. It's going to use what the model has already learned. We can do that, and the way to do that is that we can iterate over the layers. And like here, we specify that we want to make it trainable, and for every layer, that's why we have like a list of layers. We check the name. If the name starts like this one, block 5 comp 1, which is the first layer in block 5, then we're going to set this layer to trainable, and that's what we do here. If it is not, if it is below block 5, then this layer is not going to be trainable, which is false here. That means it's going to be freeze. So after we do that, we basically build the model from bottom up. We connect to the dense layers. Here's the architecture, and then we fit into the generator. So let's scroll down and see how the accuracy of the validation, which is pretty good now. So it's basically, yeah, it is amazing. Like, you see the accuracy here and here. So same thing for the last 20 epochs, the accuracy was really good. So we can use the evaluation generator for the valid generator and also for the test generator, and the accuracy is amazing. And this is how you build a convolutional neural network to classify images. You can either build it from bottom up, from scratch, if you have thousands of images, or you can use a pre-trained model if you have a small data set, and then with the pre-trained model, perhaps you can update the weights of some of the layers. And yeah, just remember, like, at the end, you're gonna have to add a dense layer. So there is something that I want to add that I don't want you to forget. And there is one big difference between a dense layer and a convolutional layer. And let me make a note here. So let me put it like this: note. the weights in convolution layers are shared Wires in convolutional layers are shared while dense layers are not. Okay, this is all, and